design of a digital modulator consists on the selection of M signals to be associated to the M symbols that we have in an M80 system. In this video, with a very simple example, we will see that to select these signals working in the continuous time domain of the signal representation is unfeasible. In this case, we have a very simple example, a binary system, so we only need two signals to implement the modulator, S0 of t and S1 of t, and we have four possible candidates, four pairs of S0 and S1. The first set of signals, we have square signals, signals with a constant amplitude in the duration of the symbol interval, which is capital T seconds. One with amplitude +1, S0, the other one with amplitude -1, S1. In the second set, we have something similar, but now the amplitudes are +2 for S0 and 0 for S1. In the third set of candidates, we have a cycle of a sine function in t seconds with amplitude square root of 2 for S0, and for S1 we have minus this signal, the same signal but inverted. And in the fourth set of candidates, we have a cycle of a sine with amplitude 2 for S0 and a cycle of a cosine in t seconds, again with amplitude equal 2. We have four sets of candidates, very simple signals, and even for these simple signals, we will see the difficulty of working in the time domain representation of these signals. Basically, in the selection, three factors must be taken into account. First, the difference between the signals, because the higher the difference between S0 and S1, the better the performance. Then we need to know the energy of each signal, and the lower the energy, the better. And then we need to have signals that are appropriate, that are adapted to the characteristics of the channel that will be used for the transmission. To quantify the difference between signals, for instance, it's possible to define a distance measure that is proportional to the energy of the difference between the two candidate signals, between Si and Sj, in this case between S0 and S1. It is straightforward for these very simple sets to compute that the four sets have the same distances. The integrals here are very, very simple. Then we need to compute the energy of every signal, and the average of these signals is the mean energy per symbol, that is a measure quantifying the energy of the set of the candidates. In this case, for set 1, it's easy to see that the average of the energy between S0 and S1 is T, for the set 2 is 2 times T, for the set 3 and 4 are again T and 2 times T respectively. For these four sets of relatively simple signals, it's easy to compute the difference between signals, the energy of the difference. It is easy to compute the energy of every signal. But in any case, it's unclear how to modify the signals to take into account the trade-off between difference between S0 and S1 and the energy, because we want to maximize the difference, but at the same time we want to have the lowest possible energy. It is unclear how to trade off between these two parameters. Moreover, if we want to modify some of the signals, it's necessary to take into account their response, because this response must be adapted to the characteristics of the channel that is used for the transmission. For instance, sets 1 and 2 can be used for baseband transmissions because the frequency response of square pulses is centered at 0. And sets 3 and 4, we have sines or cosines of frequency 2 times pi divided by t radians per second with a single cycle in t seconds, And these signals could be appropriate to transmit in a bandpass system whose center frequency is 2 times pi divided by t. But to take into account, working in the time domain, difference between signals, energy of every signal, frequency response of every signal simultaneously, to modify them, finding a good trade-off between the 3 parameters is really, really complicated. Everything is much simpler if a vector representations of the signals is used in the design of the modulator, because a signal can be represented by a vector of capital N coordinates, and the signal can be written as a linear combination of these coordinates times the n elements of an orthonormal basis. And the good property of this representation is that the energy of a signal and the difference between signals measured as the difference between the energies, as measured by the energy of the difference between the signals, can be obtained by the norm of every vector and by the distance in the vector representation of these signals, independently of the shape that we have in the time domain. This shape is only related with the orthonormal basis that is used to implement the signal from the corresponding coordinates. Therefore, it's possible to take into account the trade-off between difference and energies in the vector representation using the constellation, the coordinates, and then to choose an appropriate orthonormal basis to take into account the frequency response of the channel. This simplifies enormously the design of the modulator in a digital communication system.